Okay, so the purpose of this lesson is just to go through a quick linear algebra review, or even just cover the basics that I think you need to know in order to understand the linear regression section of our book, and how we're going to go about doing it. So, so let's start off with the first half of linear algebra. Here, let me change that. So the first half, I should say, of most linear algebra classes, of most linear algebra classes start with the solution. So start with the solution to so what you're looking for is AX is equal to B, where A can be any M by N matrix, M being the number of rows, and N being the number of columns, slash so equations that you have, and this is unknowns that you're looking for. And then X is your vector of unknowns. So X is generally an n by 1, so it's a column vector. So it has n rows in one column, so it's a column vector. And generally, that's how we show vectors in this course and in linear algebra class. So it's a column vector of unknowns. And then B is an m by 1 column vector, generally given. It's sometimes referred, so sometimes you'll see it referred to as the right-hand side, RHS. So you'll see right-hand side. In general, the solution to this AX equals B, it can have one solution. So if you were just to randomly pick an A and a B, in general, you would have one solution. You could have no solution, or you could have an infinite number of solutions. So the one that we're going to concentrate on today is the no solution. So let me go ahead and highlight that one. So this is the one that we're going to talk about once we get to talking about linear regression. This is the one that we're going to be referred to, or to be talking about, is when we have too many equations and not enough unknowns. So here's an example of what one of these might look like, and I'm just going to do an n by, so our square matrix, a 3 by 3. So I'm just going to do a 3 by 3, and we'll give you 1, 1, 2, 2, 3, 1, negative 1, 2, negative 2, and then my vector of unknowns, x1, x2, x3. So this is m and n. And so we know this will be a 3 by 1, and that's going to be equal to some vector, the right-hand side, 1, 2, 3. You can see my imagination going wild here. But I'm only showing this because I want to show another way that we could write this. So another way that we could write this system of equations. So this is this would be your matrix A, this would be your vector X, and this would be your vector B, and this would be your matrix multiplication sort of version of this. Another way that we could write the same system of equations is a system of linear equations. And all we do is multiply this thing out. So it's just 1x1 plus 2x2 minus x3, or minus 1x3 is equal to 1. So that'd be the product of multiplying this row by this column and setting it equal to that number. And we do the same thing with the next row. So you come down here, 1x1, 3x2, 2x3 is equal to 2. So if you continue this sort of pattern here, so 1x1 plus 3x2 plus 2x3 is equal to 2. And then the last one, then you would have a system of linear equations, and that's okay. Another way to do the same exact thing, and there's a reason why we sort of need to see these different ways of writing it. So if I just looked at this one column here, then I could have 1, 1, 2, and we can multiply that by x1. And then we looked at this column, right? So I have 2, 3, and 1. 2, 3, and 1 times x2 every time, and then plus this last one, obviously, so negative 1, 2, and negative 2 x3, and that is going to be equal to the vector 1, 2, 3. So this way of looking at it is, so these are the columns of A, so this is so this is a linear combination of the columns of A, of the columns of A that give B. So in this case, the solution, x1, x2, and x3 is the linear combination of the columns of A that give B. So it's another way of looking at exactly the same problem, and it's very important that we understand this way of looking at it as well. Okay, the next part is let's talk about what linear combinations are real quick. So we're gonna just, the first one is the first part here. So if we just looked at this, and I'm taking the vector 1, 1, 2, and we're multiplying it by x1. So what happens to the vector 1, 1, 2 when I do what's called scalar multiplication? Scalar multiplication. And this happens regardless of the dimension. So in this case, we're a 3-dimensional vector, but it could be a 2-dimensional, or not one, 4-dimensional, whatever. What happens when we multiply by scalar multiplication? So I have a vector, and we'll let this be 1, 1, 2 in 3-dimensional space. And then what happens when I multiply by a number that's less than 1? All it does is it makes it so we'll let x1 be between 0 and 1. So that's what it does. It just makes it a smaller version, but it still points in the same direction. If we multiply it by a number greater than 1, then we're still going to point in the same direction. And this is x1 is greater than 1, but it's just going to be longer. If we use a number that's less than 0, so maybe we're pointing out that direction, so x1 is less than 0, then you're still on the same, I want to make sure that we get this, we're still on the same line, so it's parallel. All these vectors are parallel. It's just you're pointing in the opposite direction than the original vector 1, 1, 2. So that's really what happens with scalar multiplication. Is all it does. So scalar multiplication simply changes the size of the vector, or opposite direction. opposite direction / size if it's negative. But you're still in that same line. All these vectors are what's considered parallel to each other. The next part is vector addition, right? So that's what we're talking. Again, we're talking those linear combinations. And what is a linear combination? If you come back over here, it's a scalar multiplication. So all I'm doing is taking this 1, 1, 2 and making it bigger or smaller. But then what's happening when I add it to other vectors that I'm making bigger or smaller? So that's kind of the idea here. Is so if I give you a vector, let's see, what does it look like? So if this is the vector A, and this is the vector B. The question is, what is C is equal to A plus B? So if I'm going to add those two vectors together, what does it look like? Matter of fact, I'll just change the color. We'll call it C and make it green. And so what it does is if you do this tip to tail business where you put the second vector on the tip of the first vector and then just have it go off in that direction, then you can go to the tail of the first vector and go to the tip of the second vector, and you can get that vector. And hopefully this is a straight enough line. So this would be my vector C. So C would equal to A plus B. Now the reason why I point this out is because we're going to need to look at a different. So we're going to need to know this first in order to understand the next part. So what would C minus B equal, right? So remember, all we're doing here is scalar multiplication. So in this one, we're just multiplying by a -1 here. Instead of C plus B, we're doing C times a -B. So if we were doing the tip to tail, we'd come here to if it was plus B, then the B would obviously be going off in that direction. But I'm doing -B. So what happens to it? So it just has the same exact length, but it just points in the opposite direction. So that's what the minus B does. And so what would that be equal to? Well, it makes a lot of sense too. So if you look algebraically, you get C is equal to A plus B. And then what happens when I subtract B? I better get A. And so if we did the tip to tail method here, we would see, here, let me use another color. Let me use orange. I would see C goes up to here, and then I would take -B and put it on the end of there, and we would get back to A. So that makes a lot of sense as far as how these things are, how algebraically and geometrically. So I just wanted to point that out. Use the tip to tail method, understand the tip to tail method, and we will need that here when we set up the linear regression problem. The next part is talking about orthogonal. So orthogonal vectors. What does orthogonal mean? They're 90 degrees to each other. That's simple. So if I gave you two vectors, let's see, this one's here, this one's here, they're 90 degrees to each other. So this would be A, and this guy would be B. Let me just give you one. I mean, I'm not drawing these to scale. I'm just giving you two vectors that are orthogonal to each other, -2 and 1, and B is equal to 1, 2. Then A dotted with B would equal. So what is the A dot B? It would be 1 times -2 plus 2 times 1, which would be equal to -2 plus 2, which is 0. So that's the key piece here, right? So if I give you two orthogonal vectors, A is orthogonal to B, regardless of the dimension, then A dotted with B must equal 0. Okay, last thing is to know that the dot product, A dot with B, can be written in matrix vector / matrix multiplication form doing this. So I could take the vector A that we know is a column vector, turn it into a row vector, and then multiply it by my column vector B. And so let's just see that real quick. So in this case, A was -2, 1, and then so we turned it into a row vector, and then I multiply it by a column vector. So this component times that component. So matrix multiplication, or how we do it with matrix multiplication, this row times that column gives us -2 plus 2, which is 0. So that's a way of doing it. And then of course, we could do it the other way as well, because it doesn't matter which one you do put transpose and multiply. You're still multiplying the same two components and adding them together is equal to 0 as well. Okay, so that's orthogonality. The last little before we start introducing the last little tidbit of linear algebra. Now, there's a lot that we could go into, but I'm just trying to introduce the minimum amount possible in order to understand this idea of least squares, is the transpose. And so we need to know what happens when I get these two matrices I'm multiplying together, or it could be a matrix and a vector, but I'm going to do the transpose outside of the parentheses. Well, how do we distribute that inside? The answer is B transpose, A transpose. So you reverse the order. But the easiest way to see that, and so I'm not going to go into any proofs, but I'll just show you the easiest way to see this is to look at the dimensions. It's just to look at the dimensions. And I think hopefully that'll make a lot of sense to you. Look at the dimensions. And what do I mean by the dimensions? Let's give you a couple matrices, right? So I'm going to say A is a 2 by 3, and then let B be a 3 by 4. Obviously, I want to be able to multiply these two so that the number of columns in A needs to equal the number of rows in B. And because of that, then we can multiply those two matrices together, and we're going to get out a 2 by 4 for AB, but then when I transpose it, we will get, so AB transpose, so inside here will be a 2 by 4, but this whole thing, once I transpose it, will be a 4 by 2, because we turn the rows into columns and the columns into rows. So let's see what happens if we didn't reverse the order, right? So in other words, I had A transpose times B transpose, right? So remember, A was a 2 by 3, so the transpose would be a 3 by 2, and B transpose would be a 4 by 3. So hopefully you see that we're running into an issue right here, right? So my number of columns in A does not equal the number of rows in B, so we have issues. You can't even multiply these two matrices together. So this is a big giant red X. Cannot do this. Doesn't even make sense. So the question is, can we at least multiply if we reverse the order? So B transpose, A transpose, and let's see what happens. So if I get B transpose, I know that's going to be a 4 by 3. So this is a 4 by 3. And I do A transpose, I get 3 by 2. Right? And so we get those two line up. So now we know we can at least multiply them. And when we multiply these two, we get a 4 by 2. So B transpose is B transpose A transpose, which is a 4 by 2 matrix, which lines up with what we thought it would be. Okay, so I'm not going to go into a big giant proof about that. In general, you just need to line up the rows and columns and check it out for yourself at some point. But just know that when you, if you don't reverse the order here, you're not even going to be able to, most of the time, you're not even going to be able to multiply the matrix. You're not even going to be able to multiply the matrix. So can't do that. Okay, so that is pretty much the linear algebra review that I wanted to cover before I even introduce the idea of least squares. All right, so now we just want to introduce the idea. So introduce least squares problem. And then I'm going to come back and solve it, least squares problem using an example. All right, so that's what we're going to do. And my problem is going to be this one. I'm going to give you 3 points, and my first point is going to be 1, 3. My second point is going to be 2, 11. And my third point is going to be 3, 7. So let's go, and I want to find the best line that fits. So find the line, right? That's the idea behind this regression, this linear regression. Find the line that fits these 3 points. So let's get an idea pictorially what that looks like, or graphically. Tell you what, let me delete this. Let me put in, let's see if I can insert a shape. XY, it's not an XY, it's an X. I started in the wrong spot. Let me delete that. Let's start up here. Oh yeah, very nice. Okay, so good. So we got us an XY graph going. Now I'm going to, let's see, put 1, 2, 3, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, obviously these points are not, I mean, you can see that we're going to call this the t-axis, and we're going to call this the y-axis. And there's a reason why. I don't want to get confused, because I'm going to come back to the ax equals b problem, and I don't want the x and the t's to get kind of confused between people. But I'm going to go ahead and plot these points. So 1, 2, 3, I think that one's about right there, 1, 3. And then, let's see, let's put 2, 11 on there. So obviously it's the very top one. So that one, and then we're going to put on 3, 7. So 1, 2, 3, 4, 5, 6, 7. Go over, and it looks about right there. Matter of fact, I'm going to go ahead and delete that. And let's draw in our, let's see what color. I don't use green. Let's do purple. So, I don't know, maybe it looks something like that. So this will be y is equal to, and I'm going to use different letters, c plus d times t. So that's what I want. I want this line y is equal to c plus d that goes through all 3 of these points. But the problem is, obviously, there is no c and d. So there is no c comma d that will work for these 3 points. Why? Because they're not on the same line. That doesn't make any sense for us to, because they're not, because they are not on the same line. Okay, so it doesn't make any sense for us to look for that an actual C and a D. So I can what we can say though is we want to find the best. So we want to find the C and D that make the error as small as possible. Okay, and what do I mean by the error? So let's go ahead and write and draw in some red lines here. So these should be straight and vertical, right? And so what we're saying is these red lines are the error. I want to make that as small as possible. And not just the error, but really the error squared is what we're going to. And then why we're going to do that is because we don't want the error to cancel out. So if you're doing here, let me put a couple blue points on there. So this will be some point on the line, this will be some point on the line, and this will be some point on the line. So if you found some C and D, we could calculate what those blue points are. So let's just label it. So the blue points are the points that lie on the line, are the points that lie on the line for some C and D values, for some C and D value. So if we change C and D, the blues would be somewhere else. But what we're trying to do is find the blue point, so the difference between the blue, let's see, how do we define an error here? So it's, so error, I believe, is B minus P. Yeah, so B minus, so B, which would be the points themselves. So in other words, this 3 minus whatever that number that is. So in this case, it would be this 3 right here minus whatever number that is. Then we would go here to 11, and we subtract whatever number lies on the line, and we would come here to 7 and subtract what. So sometimes the number is going to be positive, sometimes that number is going to be negative. Matter of fact, if we do a good job, it will probably be the error. If you just added the errors without squaring it, then it would be 0. So, or there is a way to definitely make it equal to 0. Okay, so that is the problem. But the question is, well, how in the world is that a linear algebra problem? Why did I introduce any of that business? So let's look at that just for a second. So I'm going to turn it into a linear algebra problem. So turn this into a linear algebra problem. And I claim that the linear algebra is a little bit easier to solve than the calculus problem, because it's certainly a way to turn this into a calculus problem, and that's how most people get introduced to it. But it's not. It's certainly not as easy. So the linear algebra problem would be 3 is equal to C plus D times 1. Now, where did I get that from? Let's go back up. Our point was 1, 3, and our line is y. So our line is y equals C plus D. So all I did was said, okay, if t, let me come back up just a little bit. I can't get it to go exactly where I want it. It's kind of jumpy. So this was my T1, and this was my Y1, and this is my T2, and this is my Y2, and this is my T3, and my Y3. So all I'm doing is substituting 1, 3 into this y equals C plus dt equation. So that would be my first equation. My second equation would be to put the second point in to that equation, and I get 11 is equal to C plus D times 2. And then our third equation would simply be 7 is equal to C plus D times 3. So if I want to turn this into a matrix, so this is the, I mean, if you remember, we taught the systems of equations. So this is your system of equations, sort of way of writing it. And I want to turn this into a matrix multiplication. So we're going to then do, I got a bunch of 1s right here. I got a 1, a 2, and a 3 for the second vector that's in my matrix A. And then my x that we're looking for is my variables C and D. And that is equal to B, in this case, is 3, 11, and 7. Is equal to B. So if you remember earlier, we said that we are interested in the no solution. So we said we're interested in this one. And then what did we say earlier about C and D? Well, as we introduced the problem, we said there is no C and D. So there is no C and D to solve this thing. So we are interested in the best one that we can get. So there is no solution. So there's no solution. And we want to find, so we want the best C comma D. Okay. Listen, I'm kind of torn. Do I introduce the visual for this one right now, or do we wait until the next video? I think I'll wait until the next video. But that is the problem. So let me just circle the problem. This becomes the problem, and I'm going to start back at the beginning of introducing, just in case someone did not go through this video first. I'm going to start here in the next video. All right.